In this video, we continue our previous lesson. It was about derivatives using limits. If you watched the previous video, then we have defined our derivative using the limit as dy by dx, which is equal just the limit of the rate of change, which is f of x plus delta x minus f of x divided by delta x when delta x approaches 0. So basically, so this assuming that we already have a function. So let us consider the following function: y equal to f of x, any given function. And if we would like to find the derivative using the limits, so we just apply this rule. So again, the derivative dy is denoted as dy by dx, or you can also say y prime. So we will introduce these notations later. So now, so we only focus in this video and the previous video, or maybe also the next few videos about finding the derivatives using the limits. So, and this is basically, this represents the slope of the function. So let us say that we have, so let us say that this is the x-axis and this is the y-axis. Now let us say that we have this function. So, and then the slope at a particular point here, for example, x and a point x, that will give us, so this is the slope of the tangent line is basically the derivative. So the derivative represents, in this case, the slope of the tangent line at a particular point, at a particular point. So, but now let us continue our topic, which is the derivatives, finding the derivatives using the limits of a function. So, for example, let us say that just so now actually we can now introduce. So we can now introduce a formal definition of derivatives, and then we show it using the limits. So if we have y equal to x to the power n, and we would like to find the derivative of this function. So in this case, the derivative would be n times x to the power n minus 1. So this is a rule we apply to find the derivative of any polynomial written in this particular in this form. So now here, let us say that, let us restrict it and say n is not equal to 0, for example, for now. And now we would like to use the limit to show that the derivative of this function y is equal to x to the power n is indeed n x to the power n minus 1. So let us do it together. So we already know that. Just recall our definition. And this is equal to limit f of x plus delta x minus f of x, and all is divided by delta x as delta x approaches 0. So this is just the definition again. So now whenever you have a definition or whenever you have a rule, so carefully look at what is needed from here. So here we need f of x plus delta x. That means we go to our function, which is, so our function is this case f of x is equal to x to the power n. That means we are going to replace each x here, or we have only actually one x, so we are going to replace x by x plus delta x. So then we will have x plus delta x to the power n. So, and now we already have our function, which is f of x. So f of x is already given here, which is x to the power n. So now we don't need anything. So now we just replace f of x plus delta x by this x plus delta x to the power n minus f of x, which is also given here, and we'll divide by delta x. So then we have dy by dx. In this case it would be, so limit, so f of x plus delta x, then that would be x plus delta x to the power n minus, and then f of x, it is already given, so x to the power n, and then that is divided by n, by delta x, as delta x approaches 0. So now, now our task is to find this limit, or to show this limit is equal to nx to the power n minus 1. So let us continue maybe here. So now look, there are some ways of finding this limit. So the first one, we can expand, and that is not needed here. No need to expand. And other case, we can assume u to be equal to x plus delta x. That is also possible, or simply we can add x here and subtract x. The reason that we did that, this is equivalent to adding 0, right? So because we have x and we have negative x. So the reason why we did that, because we already have a rule. It says whenever you have a limit, for example, u to the power n minus a to the power n. So if we have this limit divided by u minus a as u approaches a, now here we need to be a bit careful that, so we can only use this limit when u approaches a, otherwise we cannot use it, right? So, and then the definition says this is n times a to the power n minus 1. So we are going to use this, and of course this limit we can also prove, right? So but now let us do the same here. Now if we compare, so now our limit, or our derivative that we are interested in, so that says limit x plus delta x to the power n minus x to the power n, then that is divided by x plus delta x minus x, as delta x approaches 0. Now if you compare those two things here, here it says we can only use this when we have u approaches a. That means u approaches a. But here in this case, we have x plus delta x approaches x, and this is exactly the same. But we can do it in another way. We can say when delta x approaches 0, we can also add x here, and we add x here. So this leads to x plus delta x is approaching x. So when we say x approaches 0, or we say x plus delta x approaches x, those are exactly the same. So now we can write our derivative dy by dx as follows. So we say limit, so we write everything exactly as it is, plus delta x to the power n minus x to the power n, then divided by x plus delta x minus x. So now here, instead of writing delta x approaches 0, we would say x plus delta x approaches x, right? So now you see that x plus delta x approaches x, and here we have u approaches a, right? So exactly, now we can apply our rule. So now here we have a, comparing those two, then a is x, right? So that means this limit, dy by dx, then that would be equal to, so we have n, we write n, and then we have a, which is x to the power n minus 1. So now using the limit, we show the derivative is indeed n to the power x to the power n, So n times x to the power n minus 1, this is the derivative of this function f of x or y is equal to x to the power n. So but we will continue on this, finding the derivative directly using this rule. But now let us take more examples of finding the derivatives using the limits. So for example, so let us do an example here. For example, so another example would be, so let us take this example. So if f of x equal to c, so where c is a constant, so now see, this is a constant, and we already know that, of course, the derivative of a constant is 0, and we will also discuss this later when we talk about the rules of derivatives. But now let us do this, let us prove this is 0, the derivative is 0 using the limits. So again, our definition of limits, it says dy by dx, that is equal to limit f of x plus delta x minus f of x divided all by delta x as delta x approaches 0, right? So always, again, so I repeat it many times to my students, whenever you have a rule or whenever you have a definition, so always ask yourself what is needed from here. So what is needed to be replaced or substituted? So f of x, which is already given, so f of x is given here, which is c, constant. And now what else we need? We need f of x plus delta x. So now we need f of x plus delta x. So because it is a constant function, so this is just equal to c. There is nothing here on the right hand side we can substitute. So those are two things that we need actually to find our derivative. So using the limit, then that will be equal to limit. So this is c and this is c, that means we have c minus c divided by delta x as delta x approaches 0. So this will be just limit 0, because c minus c is 0 divided by delta x as delta x approaches 0. So now this will be limit 0 as delta x approaches 0, and this is basically equal to 0. So now finally our answer, we can just rewrite it again. We say the derivative is equal to 0. So from here, the derivative of any function will be equal to 0. So I hope you enjoyed this video, and for more videos, please subscribe to my channel to encourage us to produce more videos. So thank you very much for listening.